Welcome to, and I use the term loosely, Lecture 20. So if you have 90 seconds to kill, and who doesn't, check out this tweet. It's a time-lapse picture of the elements in order of discovery filling in a periodic table. Mildly entertaining. So the song that would have been playing tonight is one that I think everyone knows when they hear it, but no one actually knows the correct name to. It's Joy to the World. Look it up, cue it up, and you'll understand. And I will save the link to today's class for the end. Last time we talked about quantum numbers and how they're related and what's a valid set, what isn't. And we talked a little bit about electron states. I like to use the word states. Other people use the word orbitals. They're kind of equivalent. So keep that in mind. The reason why I don't like to use the word orbital is because the way that most people use it, it gives you the idea that an orbital is a physical entity like a box that is constraining an electron to be a certain size or shape or energy. And that's not really the case. The electron adopts that size, shape, energy all on its own. And the orbital actually just describes what that shape actually is. So I like to use the word state because I think it's a little more reflective of what the situation really is. So for today's lectures, and there are 3 of them, we're going to talk about these things called electron configurations. All they are simply a list of how many electrons of each type there are in an atom. And for the context of Chem 1215, type of an electron means what its N and L value are. So 2p, 4d, stuff like that. And why should you care? Well, because you're going to get graded on it, but also because the types of, and that should say electrons there, particularly the last couple electrons that go into an atom actually determine its chemical behavior. Now, it turns out that when you have more than one electron in an atom, and that's most of them, that energies actually are not really pretty. In fact, technically, you can't even determine it exactly. And this is because that the electrons are sort of always constantly moving relative to each other. So you've got 3 forces here. You have the attractive force between the positively charged proton and the negatively charged electron number 1, the positively charged proton and the negatively charged electron number 2, and the repulsive interaction between the 2 electrons. And that's the one that is tricky because these guys are constantly moving. So this one can't be quantified. And the result is that this has an effect on the energies of these states, and that the energy depends on, unfortunately, not just N, but now L, which is something that we already figured out last time. All right, so energies depend on the quantum numbers, the value of the quantum numbers N and L. So in equation speak, we would just say something like this. E is a function of N and L. And it's so just to look at both of these dependencies, it's proportional to N. So, and also proportional to L. So for the same N, the energy of an S-type electron is less than that of a P-type electron, so on and so forth. So a 3s is greater in energy than 3p, which is greater in energy than 3d. And just to go back to the statement right here, so if you're keeping L constant, energy goes up with N, so a 1s is lower in energy than 2s, which is lower in energy than 3s. Now, for any electrons that have the same value of N and L, they have the same energy, and we say that those states have the same energy. We say they are degenerate, which in this case is merely a statement of energy equality. It is not a moral judgment of any kind. And again, for our purposes, we're going to call all electron states with the same value of N and L to be the same type, so the same type of state, the same type of electron. So basically, if it's 3px or 3py, 3pz, we're not going to really distinguish between those 2 states. They're all pretty much the same. And remember that in this case, px, py, and pz actually refers to the m sub l values. And just so in case you notice a difference here, in the other videos I was using a script L. The other thing you'll see is just a little italicized L like this. They mean the same thing. All right, so okay, I want to talk a little bit about the relative sizes of the various types of electrons. So we learned in the last set of videos that the value of n actually determines the size. Now I just want to reiterate, so the size, we're kind of talking about the average distance from a nucleus. And it turns out that if you look at the average distance within a same shell, they're actually a little bit different. And so the s electrons actually spend them a little more time closer to the nucleus. The p electrons are a little further out. And the d electrons even more. And the f electrons are all the way out. You will note that this is an increasing order of L values. So s-type electrons have an L value of 0, 1, 2, and 3. Now, I want to point out that the overall size of these states, the extents to which they go out into space, actually don't vary too much with L. That depends mostly on n. But if you look very carefully, there's a slight difference in the distribution between S, P, D, and F, and it's enough to make a difference in some cases. So the overall shape or the overall size of an electron depends pretty much just on n. But there is, if you look at the distribution on average, s electrons a little closer, or the closest, and f electrons are a little further out. And again, you know, these generalizations refer to the average distance and not the overall extent of the state. So the result can be a little ugly. So what this graphic here tells you is a listing of the relative energies of all the types of electrons that one finds in atoms here on Earth. So the 1s state is by far the lowest energy state. 2s is next, 2p, 3s, 3p, and it just gets really ugly right here. Now remember that this graphic here, each one of these lines represents the energy of a particular, represents the energy. Now what we need to consider when we're talking about these electron configurations is how many electrons you've got of each type. How many 2s electrons do you have? How many 3p electrons do you have? And this is just a smidge more complicated because you can have more than one 1s electron. You can have more than one 3p type of electron. So we talked about this last time when we learned about shells and subshells. And note that the number of electrons that you can have of each type depends on whether it's an S subshell, a P subshell, or a D or an F subshell. But it's consistent within each type. So S states always come in sets of 1, and that means you can have 2 electrons in each of these boxes. So you can have 2 1s electrons, you can have 2 2s type electrons, you could have 2 3s type electrons. P subshells always come in sets of 3 states, each of which can adopt 2 electrons can have each of those individual states. So you can have up to 6 2p electrons or up to 6 3p electrons. So you can have, so p electrons come in sets of 6 or no more than 6. And for D it was 10. And they're not on this graphic, but for F it's 14. So F states come in sets of 4. You can have 2 electrons of each. So that gives you the 14. So again, you can have S electrons come in sets of 2, P electrons come in sets of 6, and D electrons come in sets of 10. And that might be it for this video. I'll see you at the next one.